Hello everyone, welcome back. In this quick video, we're going to take a look at the time complexity of this insertAtPos function, and also we are going to optimize our size function to take constant time. Right now, this size function takes linear time, or big O of n, where n is the length of the linked list. So let's talk about insertAtPos function. So this statement takes constant time. This also takes constant time, constant time, constant time. All of these take constant times. If we insert at end, so this is also going to take all these statement constant times. And if position equal to 1, we insert at the beginning. We also saw insert at the beginning function takes also constant time. This also takes constant time, but once we reach at the while loop is going to loop from 1 up to position. So if the user enter position at the end of the linked list, so we gotta loop from 1 up to the end of the linked list. So in the worst case scenario, this is going to take big O of n, or linear time complexity, where n is the location of position where the user want to insert. Then these are going to take constant time. While calculating the overall time complexity of a function or an algorithm, we only consider the fastest growing term. In this case, the fastest growing term is big O of n, and we drop all the constant times, or big O of 1s. So the overall time complexity of this insertAtPos function is going to be linear, or big O of n, where n is the position at which the user want to insert. Then let's change this function. You know what, I'm not gonna change this, I'm gonna leave it, and I will define another function. Before that, let me define a variable, and let me define it as private int length, that shows the length of linked list, length of the linked list. So when we first create an object of this linked list, so I'm gonna set this length to 0, meaning that we don't have any item at the linked list so far. So I'm gonna create a new function, public int, let's call it length. It's going to do the same as size function, but this time it's going to take a big O of 1, or linear time complexity. We just want to return this dot len. Okay, it's same as size function, but I'm gonna keep both of them just in case. So every time we insert in our linked list, what I'm gonna do is I will increment this len function. So I insert here, insert at end. So if linked list is empty, I insert at the beginning of the linked list, so I increment the len attribute. Then else I'm gonna insert it, increment it here. Then let's take a look at insert at the beginning. If list is empty, increment the len variable, else also increment it. Then we insert at position. So if position, okay, we insert, you know what, instead of this, because if the user enters at the end of the linked list, it's also going to take big O of 1. So if the user choose to insert at the end of the linked list, we can make it take big O of 1, or constant time complexity, by just calling insertAtEnd function, and we pass the data. Once we inserted at end function, we just return. We don't want to calculate these other statements. So if the user choose to insert at end of the linked list, so insertAtPos function takes constant time, since insertAtEnd also takes constant time. So insert at beginning. Okay, once I insert it here, again I'm gonna increment the len function. I think that's all. Let's check the len function also. After this, I'm going to print len. List.len. Let's run the program. Length is 7 and size is 7. Insert at the beginning. Let me insert at the beginning in list.insert. At the beginning, say I want to insert 100 at the beginning of the linked list. I inserted 100, size is incremented and length is also incremented. Thank you guys for watching and see you in the next video. Bye bye.